start now because it's
Yes, yes.
3:30
Let's.
and
We can start now.
yeah, okay. So let us start. Today is the 11th edition of our webinar series from the GamesNet team, and we are privileged to have Professor Tamer Basar from University of Illinois Urbana-Champaign with us today. Professor Basar received his BSEE degree from Istanbul Robert College and MS, MPhil and PhD from Yale. He is currently teaching at Urbana-Champaign and he holds the Swanland Endowed Chair, Center for Advanced Study, Professor of Electrical and Computer Engineering, Research Professor at the Coordinated Science Lab, and Research Professor at the Information Trust Institute. Apart from that, he holds numerous prestigious positions in the academic world and editor or co-editor of various journals and other academic publications and recipient of numerous awards. In fact, I can see that he has a staggering over 900 publications in a wide array of subjects. So I think I am speechless and I would immediately hand over to Professor Basar so that he can start his talk. So Professor Basar, once again, very warm welcome from the GamesNet team. And I would request all the attendees to go on mute. Professor Basar, over to you.
Yes, yes. Thank you very much for the invitation, and it is at the end. So now I know that everyone is in the mute mode, and at the end I'll leave some time for questions, and if anyone has any further question, then they can write to me, and if they're interested
would you mind taking questions in between, or should?
Oh yeah, I can take questions in between also. Sure, if that can be arranged on your side, yes, definitely.
What we'll do is we will try to track the chat box here. And
yes, yeah, sure. If there are really urgent questions which is for clarification at any point, then please, yes, I can take questions also as we go along. So the topic I know that your group is on games and networks. So I picked a topic that we have been working on for many years now, and this is a sort of a new trend in game theory, and there are elements of networks also here, even though I won't be talking much about networks, but that's implicit as far as the structure goes. And I'll also bring in some elements of robustness in two different ways, as you will see. So here is the outline of the talk. I'm going to give a general introduction to non-zero-sum stochastic differential games, and the Nash equilibrium as a solution concept there. And the important thing when you go from single agent optimization problems to multi-agent scenarios is the emergence of strategic interactions between or among the players. And also the role of information structures. Information structures play an important role. And this is all known. And but this makes a derivation of solutions for a very large class of games, obtaining the Nash equilibrium quite difficult, and in some cases even impossible. And so to circumvent that difficulty, or to overcome that difficulty, people have started looking into, I mean, there are different ways, but provide a brief introduction to the mean field approach and why actually that has been introduced in this context, and where it applies. Of course, you need some structural sort of conditions. And then I'm going to bring in the robustness element. And this is, you can bring robustness in two different ways. You either change your objective function to a risk sensitive one. And so I'll provide a quick overview of the risk sensitive stochastic control formulation, because each player, in this case, if a player has a risk sensitive cost function, then they will be solving a risk sensitive stochastic control problem. And then I'll talk about an equivalence of that formulation to zero-sum stochastic differential games. So even for a single agent, and then there will be extensions to multiple agent problems. So one brings in a sort of a virtual player, an adversarial player, and solve a zero-sum game instead of a single optimization problem uh, in the case of single agent problems. And then I'll of course talk about the multi-agent versions of that. And then I'm going to, because of that equivalence, there are two different ways of approaching uh, uh, robustness issues in mean field games. And one is through risk sensitivity, and the other one is through um, this zero sum approach by bringing in an additional virtual player who goes against the other players. And then I'll discuss the equivalence between those two. And then going from the mean field to a finite mean field entails an infinite population of players. And from there, I'll go to a finite population and show that there exists a Nash equilibrium, but not an exact Nash equilibrium. It's an epsilon Nash equilibrium in that case, and then talk about some extensions and conclusions. So here we are, a general non-zero sum stochastic differential game will have, you have to specify the number of players. And here I take capital N players. And then you have to specify the objective function for each player, as well as the information structure. So that's the sort of the description of a game. So I'm going to assume that in this overview, there is a high dimensional stochastic differential equation, which captures the evolution of the game. And then so this is a compact notation. The U here is not controlled by a single agent, but it's controlled by multiple agents. And in fact, it has its components, U1T through UNT, where the U1T is controlled by agent one or player one. I'll use these terms interchangeably, and so on. So you can, and then X0 is the initial state, and B is the Brownian motion in this case, and it's a vector valued Brownian motion or Wiener process. And so this is a stochastic differential equation. Of course, the evolution is not complete unless I tell you what U the control depends on for different players. Now, I mentioned about networks, and it's this is an sort of a composite form, but it is in many applications you have individual local state dynamics for the players. So in this case, for the ith player, I have a lower dimensional, definitely, state dynamics, and note that this has the control of the ith player, but also you have the controls of the other players as well as the states of the other players, which enter in some form. And minus I means the controls of all the other players except the ith one. and likewise the notation xi is used. And this is the Brownian motion that enters into the state equation of the ith player. Now, so this is if I didn't have this term ci in this case, then this would be a decoupled system. So it means that this first one is decoupled completely, and each agent has its own dynamics. Then that would still be an interesting game, but you have to bring in some coupling, and the coupling in that case is brought in through the objective function. So to make any formulation a genuine game, you have to have either coupling with some of the players' controls or states through the state equation, or you have to have coupling through the objective function, which I'll come to shortly, or both. And note that so this is the networking element will come in here, is that this coupling could be only with the neighbors. So you introduce a topology for the network where you can introduce neighborhoods for different players. And so if I denote the neighborhood of player I by script ni, then it's essentially the players in that neighborhood are coupled in their decisions, in their states, with player I. Okay, so you can have a more, and this is captured through C sub I, as well as through the objective function, coupling through the objective function. So this way you can bring in a networking aspect of the problem.
Professor,
So,
can I
yes,
ask? So, just two quick clarification. In the second formulation, if
right.
suppose I assume the neighbor of ni to whom I is interacting, in that case, this x minus I is the component of the ith neighbor. Is it correct to say? Or
Yes.
okay.
That is the assumption is that the CI is defined in such a way that
It depends only on the neighbor.
it only has the states and controls of agents whose indices are in NI.
Okay. Yeah.
Otherwise, it's
The other clarification. So far the payoff function of players are not defined yet, right? Or
no.
am I?
I'm coming to that. It's
Okay.
all
Okay.
on this
Well,
slide.
thank you.
But I'm slowly
Okay.
introducing
Thank you. Sure.
the ingredients of the game. Yes.
Thank you. Thanks.
And this is a general structure. I'm going to talk about some special structures also later on. So this is introducing games in general. So information structures. You can have essentially a player I can have access, again, if we talk about this composite form, where X is actually the states of all the players, then a player could have access to the state of his own state as well as states of other players. And this is known as the closed loop perfect state information for all players. And it could, in fact, even involve memory. And so this is a problem if you have this type of an information structure. It's relatively easier to solve the game. At least one can write down a set of sufficient conditions, as I'll shortly describe. Now, somewhat more difficult, but definitely much more realistic case would be when each player has access to its own local state and also the history on it, but does not know anything about the states of the other players. Now, one generalization of this would be, and I haven't included it here, a player could have access to the states of only its neighbors, but with some delay. Okay, that would be a delayed partial state information. Now, Another information structure would be the one which involves measurement feedback. Each player would have a channel through which it obtains information that depends on its own state, as well as in some form the states of other players. And so this is, again, the BI is a Brownian motion here. And so this is a measurement channel, and a player would, and different players could have different measurement channels. And this is the most difficult problem, actually, as far as game problems are concerned. And then each player has access to its own measurement and also the history of that measurement. And then, of course, again, in this case, you can have a player could have access with some delay to measurements of other players in its neighborhood. Okay, now coming to the loss function. The loss function of a player over some given interval, T capital T, and that could be also an infinite interval, is given in the familiar form in optimal control, and where there's a terminal cost, and then there is an integral cost here from T to capital T, where T, of course, what a player wants to minimize is the cost going from T equal to 0 to capital T. And this depends in general on the state of that player, as well as the control of that player, as well as the states and controls of other players. So in other words, I haven't written this down I haven't broken this into specific dependencies on the states and controls of the other players, but you will have to assume that in this formulation, it actually corresponds to this general one, where the X is the composite states of all the players. And then I'll have some more specific information, specific functions later, where it depends only on some aggregate quantity as far as the other players' states go. So now, of course, this is a stochastic quantity. You have to take expectations over this. And that defines, and then together with the information structure, the information, essentially the way you generate the control is by applying a mapping that's consistent with the information structure of the players, of each player, on what is available to them. So once you substitute all that in, assuming that these stochastic differential equations have unique solutions, then you have a function for each player, a deterministic function, which is a function of the policy. So this is the policy or control law of the ith player, as well as the policies of all the other players. Okay, and then in this context, you can introduce the notion of a Nash equilibrium, and which I'm sure to this community it's all well known. So this is, once you bring it into this form, then it's, at least conceptually, it's very easy to introduce the Nash equilibrium. And so you are the start quantities, the policies are in Nash equilibrium if you hold everyone fixed except the ith one, and the ith one minimizes his own cost, and in this normal form of the game, and then you obtain the gamma sub I is the set of all policies consistent with the information structure. So again, so this is my second slide. The first part is what I had on the previous slide, and as I indicated or alluded to, if you have closed loop perfect state for all players, in other words, everybody shares everything, the states, then as if DD transpose, that's what multiplies the Brownian motion, is strongly positive. So which means that the noise penetrates through all channels, and so there is no deterministic part of X. Then one can show that the Nash equilibrium exists and is unique, but this is an indirect condition, if a coupled set of PDEs, partial differential equations, admit a unique smooth solution. Okay, so people have looked at the, so at least conceptually it's clear. And the other important thing here is that even though the players have access to the entire history, they end up using only the current value of X. And so therefore the controls of the players will be functions of only the current value of the state and time, of course. So there have been many attempts at, depending on the structures of F and G and so on, in trying to solve this numerically, but for some classes of problems, one can in fact obtain explicit solutions to this as well. Now, if I have other types of dynamic information structures, which is not consistent across the players, and the players are interacting with each other, like you have local state information or decentralized or measurement feedback, the problem is extremely challenging. And in fact, there is no hope of obtaining unless you have very special structures. And I'm not including open loop solutions, which are not of interest, especially for stochastic problems. It's a very challenging problem to obtain the Nash equilibrium, and the solution is probably infinite dimensional if one can obtain it, even if the Nash equilibrium exists and is unique. And even in linear quadratic problems, which I'm going to address shortly, the problem is extremely challenging. And why? The reason is the strategic interaction among the players. So what happens is that if players do not share the same information, they will try from what they observe. Note that an important aspect of these game formulations is that there has to be some coupling between the players, either through the state or through the objective function, or both. Let's say that you have a coupling through the state. And let's say that you have only two players. One of the players, let's say player one, has developed a policy which depends only on his own state, local state. And now player two observes his local state and he has access to this information. But also from there, if that player knew what the state of the first player was, then he would be able to improve his performance index. But that information is hidden there, in a sense, through the coupling. So there is the second guessing phenomenon that comes into picture. And this is sometimes known as infinite second guessing because there is no end to it. So a player will have to second guess the information available to other players, not to her, in her active neighborhood. And as it could be useful to that player in improving her performance, as I indicated. So players do this, then this leads to an infinite recursion and leads to an asymptotic learning of the relevant information. And the question is, can you asymptotically learn everything? And through strategic interactions or part of it? And this is really an open question. And the problem is, in fact, not even, one cannot even come up with these infinite recursions and a mathematical analysis of where that leads to. So with asymmetric information, this is what we would call also asymmetric information, there is the second guessing phenomenon which makes the problem quite difficult. Now, I mentioned linear quadratic non-zero sum games, and then so here is just for reference, you have linear dynamics, and this is known to all of you, and then quadratic performance index for each player, and quadratic function of the terminal state, quadratic function of the state at each point in time, as well as the quadratic function of all the other players. And note that I can bring in a neighborhood structure here if I want to, through the B sub j's. So for each player, I can assume that, of course, I have to partition X into that, but I'm not doing it because here I'm assuming that all players know all others' states. So the X is accessible to all players. And likewise, by the choice of IIJs, you can either weight only the ith players control here, or you could have a weighting over other players in a neighborhood of I. So this problem admits a feedback Nash equilibrium. So I had this coupled partial differential equations. So those can be solved explicitly, and turns out that these are quadratic plus some constant term, and the quadratic part is defined through some Riccati equations as an optimal control. But the part that's difficult or different is that you have coupled Riccati equations in this case. So that makes the solution of these Riccati equations difficult, but still this is an offline process, not an online process. And the solution is linear whenever one can obtain solutions to these Riccati equations. And one can use sort of fixed point algorithms or fixed point theory in order to show existence and computation, come up with computational schemes for these Riccati equations.
Professor,
Now, yes.
In this setup, what is the definition of Nash equilibrium precisely? Have you?
The Nash equilibrium is exactly the same I had earlier. So what that essentially means is that if all players admit this, use this policy,
this policy. Okay. So
except the ith one, and the ith one minimizes this, then his solution is going to be linear. And that's a result from optimal control theory, because once you fix everything in this form, substitute this in here, this becomes a linear quadratic regulator.
Got it. So strategies of players are the policy functions.
These are policies, yes. Strategies of the players are the policies, and there is no infinite recursion in this case, because once everybody except the ith one picks this, then the ith one will also have to pick this.
Thank you.
There is no learning coming. So the question is there any, so when you have local stated information and so on, even in the linear quadratic case, this is quite a difficult problem. And the question is whether there is any hope of obtaining the solution when n is sufficiently large. And the answer to this is provided, and this is one of the reasons why we work on mean field games. The mean field game theory provides the answer. So before I make the connection, let me share with you, going back to the origins of game theory, and everybody would acknowledge that the game theory was introduced or was introduced to the world scene, to the scientific community through the book by von Neumann and Morgenstern, and that's the theory of games and economic behavior. And this is 1944 edition, pages 13, 14. They were interested in solving some class of games, not the ones that I have here. Differential games had not been introduced yet, but still they encountered problems when there was a large number of players. And then they said, when the number of participants becomes really great or large, that's great was the word they used, some hope emerges that the influence of every particular participant will become negligible, and that the above difficulties may recede, and the more conventional theory becomes possible. And then they go on to say that it's a well-known phenomenon in many branches of the exact and physical sciences, that particularly, for example, the thermodynamics, that very great numbers are often easier to handle than those of medium size. This is, of course, due to the excellent possibility of applying the laws of statistics and probabilities in the first case. So this is an insightful sort of observation. And the question is, can we come up with structures, which also make sense, where when we go to the limit, take the number of players to infinity, then we end up with a simpler sort of classes of problems, simpler in the sense of if we try to obtain the Nash equilibrium, for example, we can obtain that. And then hopefully we can use that solution for the finite population case. Okay, so this leads to the following formulation for mean field games. Now you have to have, as I indicated, you cannot have the most general structure. You have to have a specific structure. And let's say that the local state dynamics of a player, ith player, is given in this form. Now note the special structure here in f sub I. It depends on the state, the local state of that agent. It depends on the control of that agent, or agent I. And then, as I indicated, that you have to have some coupling in order to make the game a meaningful one. And then it depends on some term, which is the average of the states of all agents. Here you can, it could be the average of all other players except the ith one, but if n is sufficiently large, it doesn't make much difference. So for all practical purposes, we include the ith one here as well. And you can also have the sort of the average of the controls of all the other players, but generally in applications, the coupling is through the states, through that average state. And this is known as a mean field term. And because we know from this law of large numbers that as n goes to infinity, if you have a large number of these, then this may have a well-defined limit. And the important thing is that that well-defined limit does not carry any specific agent-based information. And so therefore, for an agent I, there's nothing to learn about the states of the other agents, and you don't in fact need to learn anything about that. All you need is the limiting of this quantity, and so I'll come to that how one can do it. So the cost function of the as I indicated, you can have couplings between the players either through the cost function or through the state equation or both. So here I also have the same term, the so-called mean field term, appearing in the cost function of the players for agent I. So, so what's the approach to problems of this type? You treat xn as a fixed stochastic process, and this is known as the mass behavior. So you have individual players, states, are contributing to this term xn, but what one particular player does, if n is sufficiently large, if he changes or deviates from a particular strategy, it's not going to make much difference, in fact, no difference at all when n is very large or infinite on this term. So this term is not affected by individual deviations by the players. So therefore, the hope is that this xn could be computed in advance, could be viewed here as an exogenous process. So what you do is, so once this is an exogenous process, then you do not have the coupling between the players will be only through this exogenous process. So if you have this, then each player faces a stochastic control problem, okay, given x and t. And so therefore you can use the methodologies and the tools of stochastic control to solve that problem. And the state equation in this case is what's known as the Makin-Vlasov equation, because it's driven not only by pointwise states and controls, but also by the distribution of x and t. And so you solve the stochastic control problem, and then you substitute it back. Note that that stochastic control problem, the solution for ui is going to be a function of xi, as well as it will depend on this term x and t. So you substitute it back into x sub I, and then that leads to a Fokker-Planck-Kolmogorov forward equation. And what you need is you need a consistency with Fn. This is what I call Fn, which is fixing Xn as a mean field term. I denoted it by Fn. But note that you need consistency. You cannot pick Xn arbitrarily or Fn arbitrarily. After you solve this stochastic control problem for each agent, when you substitute the resulting x sub j's into this equation, which depends on what you picked as Fn, then then Xn will be Fn depending on Fn. So there is a fixed point equation. So that the solution of that fixed point equation will lead to the corresponding relevant selection for the x and t, and then that solves the problem. And then so that's the solution in the infinite population. And then what one has to do is come back and study the relationship between finite and infinite and solutions that leads to an epsilon Nash equilibrium. So what that essentially means that now I have a solution for under the assumption that we have infinite number of players, and let's say that each player adopts that solution. To what extent is that an equilibrium in a finite population regime? And that leads to what's known as an epsilon Nash equilibrium. In other words, it's close to the Nash equilibrium of the original problem, of the original game, which we cannot solve. So this way, it's possible to obtain the solution to games with local information. And note that any solution that we obtain, since the stochastic control problem that we solve here is a function of xi, and this fixed term, which is the solution of a fixed point equation, it uses only local information, local state information, which we know we cannot solve for any finite population game. But this is one way of obtaining an approximate solution. This was a research initiated by mean field, not in this general sort of framework, was initiated by almost simultaneously by two groups. Laszlo Lyon's a paper which appeared in the Japan Journal of Math in 2007, and in France. And their motivation was solving partial differential equations, not the way I presented it here. And then an almost concurrent paper by Juan Keynes and Malhame from Canada, which appeared in the Transactions on Automatic Control in 2007. So these are the historical things. Now I want to come back and, well, not come back, but talk about a little bit risk-sensitive formulation. And because I want to bring in a robustness element. So let me first ask the question, can I go a bit over, or is it, should I stop exactly at 1 o'clock, in 1 hour?
I guess let us go on till 8:35 or 8:40 because we started a bit late.
Okay, sure, sure. So I'll take an additional 10 minutes from what we had. Okay, so the risk sensitive formulation, you replace, so this is the for general non-zero sum games. So this is was the loss function. So what you do, I'll quickly go over this. And you multiply it by some parameter theta, and and then take the exponential of this, and then take the expected value, and then take the logarithm to bring it to the same sort of level, and then multiply it by 2 over theta. So if this were a deterministic optimization problem, of course, this is inconsequential because there is no expectation, and then the logarithm is the inverse of the exponential. These cancel out, and then you would be just minimizing L sub I. But if you have stochastic problems, then this makes a big difference. And the theta is a positive parameter, is known as the resistivity parameter. And this is the degree of pessimism of a particular player. Now you can have theta indexed by I, different players could have different sensitivity indices. And so this is the L sub I. And the Nash equilibrium, so once I bring it into this form, it's in normal form. Nash equilibrium is, of course, defined in exactly the same way. So the question is, can we obtain the Nash equilibrium, and what for this problem, and what does risk sensitivity bring? What do we buy by going to this exponential cost? The best is to go to look into the stochastic control problem in this context. And the state dynamics is given in this form. Again, Brownian motion. I have a square root of epsilon term here because you'll see the role it plays. If epsilon is 0, then this will be a deterministic problem. And so what we want, again, the exponentiated cost, but here there's only one agent. And L is given in this form, what I had earlier. And so you can apply dynamic programming to this problem. And first write down the dynamic programming equation associated with this before you take the ln, and then use that, the relationship between the psi and v, which is the value function associated with the original problem, which is the logarithm of this multiplied by 2 epsilon over delta. Now, this is the important thing here is that you can obtain a partial differential equation for the value function, which depends on 2 parameters. One of them is this related to theta. It is the, I denote this by gamma, which is the gamma squared is equal to 1 over theta. And the other one is this term. So the term here is because of the presence of theta. And note that if theta is infinite, then the gamma is going to be 0, and so therefore this term is going to be infinite, is going to dominate. So what theta being very large actually means the degree of pessimism of the individual, you can view this as a single decision maker problem, is very high. And so there isn't really much that individual can do. Now, if theta is 0, then 1 over gamma squared is 0, then this term drops out. So this is what we are left with is exactly the value of the PD that we have in the standard stochastic control problem. So if we have, if capital U is an Euclidean space, F is linear in U and G is quadratic in U, then you can obtain the optimal control law explicitly in terms of the gradient of the value function. In that case, the HAB equation has this form. And again, I want to draw your attention to the presence of this term, which would not be there if we did not have the exponentiated cost. So So in addition to the, note that in addition to the normal dynamic programming Bellman equation would have the gradient of the value function and the Hessian of the value function. And in this case, what we have is an additional term. Of course, it would also have this term, which is the gradient squared. But we have another term here, which kind of neutralizes this. So this is always positive, of course. And it is possible by a selection of gamma, that's the with sensitivity parameter, 1 over gamma squared again is theta, that if theta is sufficiently large, this could drive it to negative values, and the value, the PD will not admit a solution in that case. So a further special case of this is the linear exponential quadratic Gaussian problem that goes back to Jacobson in 1973. And in that case, you can again have a Riccati solution. You can solve this explicitly and you obtain a Riccati solution, but it's not a standard Riccati equation because of the presence of this term. And what one knows is that the Riccati equation is, of course, a nonlinear equation, differential equation, which could have a conjugate point, which means that it can escape to infinity in finite time. And if this term is large, then that happens actually. So that places again a restriction on gamma, which is the degree of pessimism individuals have. Now, there is a connection between this with sensitive cost, and this is what I was alluding to when I introduced the outline of the talk, and games. So let me just quickly draw this parallel. You have a state equation again. What I have in red here is an additional term that I have introduced, and which is a second player. So this was a single agent optimization problem, but I have a second player coming in, and this is the maximizing player. But you cannot have that player act freely. There has to be some cost on the actions of that player, and that cost is captured through this term minus gamma squared, and then this is like the L2 norm and multiplied by gamma squared. And so this is now a game. We formulate this as a game, which means U, which is the original control, wants to minimize J, and this virtual player wants to maximize. And again, with full information, full state information. And so the upper value function, which is you look at the in soup of this, all policies for the mu is a policy for player 1, mu is a policy for player 2. You do this, try to write down an equation for this value function or upper value function, and which has this form. And the important thing is the final sort of observation that when you write down, it's what Isaac's condition is. For those of you who know zero-sum differential games, it means you can actually interchange the infimum and supremum. And here, because there is separability, F depends only on U, and W depends, additive separability depends, only this term depends on W, as well as this term, and G depends only on U. So there's a complete separation. And so the value function satisfies this equation. This is exactly the same equation PD that we had when we looked at the sensitivity problem for all permissible epsilon and gamma. And the same holds for the time average case, as well as for linear quadratic problems. So the bottom line here is that there is a complete parallel between the risk-sensitive control problem and a two-player game, which is formulated the same way, but with an additional input into the state equation by that new player that was introduced. You can say this as an adversary. And you can also view this as you can also view this as a perturbation, as unmodeled dynamics, for example, because W is allowed to depend even in a nonlinear way, but the worst case turns out to be linear in this case. And so this is could be the unmodeled part of the dynamics, and you are essentially developing, coming up with a control law which will be insensitive to this, or which will cope to the presence of this unknown. So now coming to the mean field. So I introduced the general mean field framework and also the robustness. So what I won't be able to go over everything here, but the question is now coming back to a linear quadratic problem. Look at it from in the mean field context. Look at it both from the risk sensitive point of view, as well as from that adversarial point of view. So the problem, the stochastic differential equation now has this form for the ith player. Now note that in this case, I'm assuming a local dynamics for the ith player, which is not affected by the state or the control of the other players. The interaction between the players will come in through the cost function. And so here is how the interaction comes in, and the mean field term is here. So the interpretation of this formulation is that each player is an individual dynamics, and then it wants to drive this dynamics in such a way that you want the state to follow the average of the states of all the other players. And every player wants to do that with some weighting factor here, matrix Q, and with some cost on control. Okay, so this is also known as a consensus problem. You want the xi to be the same or as close as possible. You cannot make it to be the same, as close as possible to the average. Okay, and so I'm looking at the exponentiated cost, and again this problem, if I approach this using sort of standard approaches of non-zero sum stochastic differential games, I cannot solve it because I'm assuming that each control has access to the its own local state and not to the states of other players, but there is coupling through the states of the other players. So that will lead to second guessing and then infinite recursion, which will not lead to anywhere. So the approach is to solve the mean field game, and then to see to what extent that provides an approximation to a finite population game. So again, this is the risk sensitive cost function. And now one thing I want to mention here is that is a form, I could have done this when I talked about stochastic control with risk sensitive cost, is that if you expand this for 1 over delta sufficiently small, okay, so here 1 over delta is the theta that I had, okay, so theta is sufficiently small, degree of pessimism is sufficiently small. If you expand this, you end up with several terms, but the most important ones, especially if 1 over delta is small, this is in the order of 1 over delta squared, which does not play in a, which can be neglected. So what you see is that by minimizing this cost, you are actually minimizing some combination, some convex combination of the mean value, which is what you would have had if this term did not was not there, which would not be there if delta is infinite or theta is 0. So it's a convex combination of the variance and the mean value. So that's what the mean field, that's what the sensitive approach does. So and then this term is the mean field term, which I had earlier, and the agents are coupled with each other through the mean field term. Now I should say that this Swiss sensitive approach to mean field games was introduced in a paper that we wrote back in 2014 with Tembin and Kuan-Yan Su. And then some of the results that I'll be presenting here were obtained with my former PhD student Jun Moon, who is now a faculty member in Korea, and which appeared in the main paper appeared in 2017 in the Transactions on Automatic Control. So let's now proceed. So again, I want to emphasize that agents are coupled with each other through the mean field term. Now the second problem is the robust control problem. Now, as I have explained earlier, the robust control problem has one where you bring in, or the robust mean field game, you bring in an additional player, a different player corresponding to each agent, and V sub I. And this theta is essentially what characterizes the ith player. The A matrix of the ith player could be different from the A matrix of the jth player. So this is a parameter that identifies the players. So you have a maximizing control here, and now we are going with risk neutral cost. Okay, so because there was a parallel between those two, and with a cost on the adversary gamma squared. And again, this can be solved using a mean field approach. You assume that this is fixed stochastic process. I have to come back and obtain the solution from that of a fixed point solution of a fairly complicated equation, but one can show that it exists. So you essentially, if I fix this term, what we are essentially going to do is for each agent U sub I, we are solving a zero-sum game. So there's an adversary interacting with that agent. And so this is a fictitious player and who strives for a worst case cost for agent I, and the agents are coupled again with each other through the mean field term. So this, let me, so this is the J1, this is J2, one is exponentiated. So this is for problem 1, this is for problem 2. So you fix G, which is the mean field term. For each one, each player I plays, so this mean field term enters into the state equation, into the cost function of the ith player. And then the ith player plays against that mass behavior. And that leads, when all players do this, then that leads to a G. And then you have to solve for the fixed point of this mapping. So this T of G is when you close this cycle. And you have to obtain a G star, which is a fixed point of this mapping to of G star. And you can, because of the linear quadratic structure, we can actually obtain the solution to this. Now we know that the two problems are equivalent, so there's only one solution here. And if we have a note that I'm dealing with the infinite horizon problem, so stability is also an issue. And so if AB is stabilizable and AQ1/2 is detectable, Let's assume that this is true. And then suppose that for a fixed gamma, there is a matrix P that solves the following algebraic Riccati equation. We call it generalized algebraic because of the presence of this term. A solution does not always exist. You need some bound on gamma. Gamma cannot be too small. Remember that 1 over gamma squared corresponds to theta that I had earlier, or delta in this case. And the gamma depends on delta over 2 mu, and mu was what multiplied the Brownian motion. So, so one can obtain the solution explicitly, and this is the form of the solution. And note that it's linear in X, and where the solution of the Riccati equation comes into play. But there is also this additional term, and the reason why we have this term is because this is driven by the mean field term. Okay, so this is the G enters here. If I did not have that coupling, then this term would not be here. And the worst case disturbance is given in this form, and one can show that S has a unique solution in the space of continuous differentiable and bounded functions. So these two, so we can call this also robust tracking problems. The two are equivalent, are identical. Now, does that necessarily mean, and note that I mentioned that you have to solve, to complete the solution. At this point, I don't know what G is. And to obtain G, I have to solve a fixed point equation. The question is, are these fixed point equations the same in the two problems? Now, we know that the solution for each fixed G, the solutions are the same, but maybe the G's are different for the two problems, the risk sensitive problem and the robust risk neutral one. And so, and in fact, it turns out that the mean field systems, that is that fixed point equation, will not be the same. So I'm going, the details are not important here. And so you can write down the mean field system for P1, that's the fixed point equation that needs to be solved. And also the mean field for P2, and the forms are different for the two. So that's where the difference comes in. And so these are TG and LHT capture the mass behavior when it n is large. And one can show that this is actually the as limit using the strong law of large numbers, that that average goes to the is the actualistic, which simplifies the analysis. It's the mean value of xi, where you take the mean value over all thetas, and then one has to solve these fixed point equations. And one way of solving fixed point equations is to see whether a contraction mapping theorem would apply, which is a sufficient condition. And so we can obtain the conditions under which that does, and these are not vacuous conditions, and you can generally obtain the solution quite through an iterative technique, as all. Whenever we have a contraction mapping, then you start with an arbitrary G here, and then find the next G, and then come back and substitute it, and so on, and this converges. And so we obtain G star and H star, and generally they are not the same. But when gamma goes to infinity, and that means that when theta, the risk sensitive pessimism parameter, goes to 0. So there is no sensitivity to risk in that case. Then this is a risk neutral problem. But then there is no, on the other hand, there is no reason why one should introduce this fictitious player either. And so therefore the problems P1 and P2 are really identical from the formulation state, not only in their solutions. And then in that case, G star becomes equal to H star. Okay. So now the final thing is if I use that solution that I obtain for the mean field game, would that solution be for a finite population? Would it constitute an epsilon Nash equilibrium? So what we mean by epsilon Nash equilibrium is the following. You fix, so this is the solution that we have from the mean field game. And so you fix everyone except the ith one, and then you obtain you minimize this. The minimum is not equal to this, but the difference is only by an amount of epsilon to the n. And the epsilon to the n, it turns out that, and this of course goes to 0 as n goes to infinity, then you have the mean field equilibrium. And this is in the order of 1 over square root of n. Okay. Now, again, I want to emphasize that this epsilon Nash strategy is decentralized. That is, ui star is a function of xi and g star, but g star itself does not depend on the states of the other players. If any player would deviate, then the g star would not change in a high population regime. And so this, we would not have been able to obtain this epsilon, even the epsilon Nash strategy, if we had taken a direct approach to the game. And so what one can also show using the law of large numbers, that the difference between the average of the states and the G star that we obtain from the mean field analysis, from the fixed point analysis, the norm of this, L2 norm of this, as n goes to infinity, goes to 0 for all t. And the lim sup also as t goes to infinity also goes to 0, almost surely. So again, G star is a deterministic function and can be computed online, and the same types of relationships also hold for T2. So this summarizes the solution, this partial equivalence that we have. And the partial in the sense that the mean field terms are not the same, systems are not the same, but the solutions are the same. And as gamma goes to infinity, then we have the two are actually equivalent. And maybe I'll skip this part. We ran some simulations for n equals to 500. And all I want to say here is that you can see that for this specific problem, these are scalar systems, and the AIs are picked as IID random variables in the interval 2, 5, and some of the others. And the gamma star in that case can be computed to be equal to 1. That is, you cannot go below that level. And then note that the G star and H star are different. Okay, so the mean field terms, that's the fixed point equation, have different solutions. And we have in the paper, you can see these figures where we have looked at as n changes, what the difference between the Fn star, the true average, and then the G star, solution of the fixed point. And fairly, for n equals to 500, it is, they are very, epsilon is very small. Okay, so I'm going to skip all this and then conclude by saying that I presented a sort of a solution to a game or a class of games with decentralized local state feedback, which otherwise, if we hadn't taken the mean field approach, we wouldn't have been able to obtain the solution. And then there are all these robustness properties that I have talked about. And so this was, the last part of the talk was on the nonlinear, with linear dynamics. You can extend these to nonlinear dynamics as well. In fact, some results on that is in this original paper, which is the first paper on with sensitive mean field games. We have fairly recent results with my colleague at Illinois and Reginsky and a postdoc we had who is now in Turkey, Naci Saldı, and where we looked at the discrete time counterparts of this, but for general, that's for very general Markov decision processes with discounted costs. And then the two papers have appeared in the one for the risk sensitive case, which is in mathematics of operations research this year, and then another one in SIAM Journal on Control in 2018. This is for the risk neutral one. And then we had the imperfect state measurements. If the players have I had that formulation at the beginning, each one receives information on his state, each player, through a noisy channel. How can you do this? Then you have to formulate the problem on the space of conditional, on the information state. And this has appeared in the mathematics of operations research in 2019. I mentioned this, but there is still a lot to be done when you have a underlying network structure where the agents interact only with their neighbors. And then there is also the class of problems where you have asymmetric structure, decision-making structure for the agents. That is, these are known as a leader-follower mean field games, where the Stackelberg solution comes into play. There is one player who is the leader, and then there are other, a high population of following players. And we have some results on this in the Automatica in the November issue. So I'll stop here. I'm sorry for going over. I wanted to give you a sort of a detailed introduction, so that took me over the time limit. Thank you very much. And I'm here to answer any questions that you may have.
Thank you, Professor Basar. It was a fantastic talk covering a lot of ground. And I'm sure that all our participants have gained a lot from attending this. Are there questions? We can take a couple. We have 2-3 minutes before we have to close.
Yeah. May I ask?
Yeah.
Yes,
Sure.
Sarvesh, yeah. Sarvesh this side. So, Professor, so I have one comment related to your last point about follower and leader. So,
Right.
as you pointed out that the solutions for in the Nash equilibrium is quite challenging and complicated. So I just want your views on that. Will this structure of leader follower, does it make it simpler or harder?
Well, it is. It's harder in the following sense. You have for each policy of the leader, you have to follow, as I indicated, there is a single leader, or you could have a leader in a neighborhood, but it has to be a high population neighborhood, and the number of followers is large. So for each leader policy, let's say that there is only one leader. For each leader policy, you are solving a mean field game among the followers using Nash equilibria. And so this is exactly the kind of problems that I discussed here. So you can view all these follower players, but then you have to take that response, that solution into account in finding the best policy for the leader. So therefore, there is this additional step which makes it more complicated. And this paper, Automatica paper, has has the solution to that. And the leader has to have also what we call open loop adapted information, adapted open loop information. Otherwise, if the leaders policy is a function of the state, then things get much complicated.
The second comment which I wanted to ask is that as you have pointed out that the complexity with the Nash equilibrium and how it's challenging. So if one makes the concept of equilibrium weaker, will that help in computing or maybe finding solutions? Could that be one direction to explore, that if Nash is
You mean for the finite population
yes,
problems?
or
I
maybe
don't
yes,
think so, because
you know,
strategic interactions are always there. I mean, you can make it extremely extremely relaxed. You can relax it by saying, I ignore completely what the other players have done.
yes, in
And
that,
but there is no, but that's not an equilibrium solution concept,
no.
because
So,
if one player deviates from that, they can definitely improve.
so to be precise, what I had in my mind is that we can make it like a undominated equilibrium where players just choose a policy function which is not dominated. So it's a weaker than Nash equilibrium in some sense.
Yeah,
So
I think the strategic interaction will still be there,
will still be there.
and
Okay.
there's no way to avoid that.
There's no okay. Thank you, Professor.
Sure.
Okay, so are there any other questions? We can take one last question from someone else. If not, then let us thank Professor Basar once again for this fantastic and illuminating talk. And thank you. And
Thank you, and I guess I should say good night or good evening to you all.
good night to us in India, and
Yes,
I don't know, good evening, good afternoon, or
almost good morning. Yeah, yeah. Okay,
thank you.
so again, as I said, if anybody has any further questions, they can write to me.